Hello, my name's Jeff Hettinger, and I'll be talking to you about some work that we've done developing iridium oxide coatings to be applied to implantable electrodes for stimulating and recording applications. This work is the result of a collaboration between our group at Rowan University and Johnson Matthey. Thousands of electrodes have been implanted over the past several decades. The use of electrodes is expected to increase due to the aging population. There are many uses of electrodes. They treat depression, they control pain, they can suppress seizures and tremors, and so on. The work that's outlined in this presentation focuses on coatings on the electrode, which both improve the biocompatibility and also the efficiency of charge exchange between the ionic solution and the underlying electrode that has electrons as the charge carriers. So by improving this charge coupling, information will be transferred more efficiently, and as a result, the electrode size can be reduced. This is a schematic of a cylindrical electrode that could be implanted in the human body. The light blue color, it represents the substrate, which is a metallic substrate and maybe is platinum iridium alloy. The blue is the coating. So in the substrate, the charge carriers are electrons, and then out here is the biological system. So that would be have charge that is contained in ionic solutions. So the inorganic materials that are typically applied to these electrodes to help enhance biocompatibility and charge exchange are titanium nitride and iridium oxide. So we're going to be focused on the iridium oxide coatings here, and the specific goal of our work is to look at the role of deposition parameter on the layer performance. So we want to improve the information exchange between the ionic solution and the underlying substrate with this iridium oxide coating, and we're looking at the role of deposition parameter in how it influences that performance. This work uses pulsed DC sputtering in a reactive environment in order to make these coatings. So here you see the parameters of the deposition, 140 kilohertz for the frequency, the period, so the off cycle is 1 microsecond, and the power is 75 watts on a 2-inch cathode. The pressure in the chamber totally is 15 millitorr, and the cathode to substrate distance is about 3.5 inches. So here represents a coating at 3 different magnifications. So it's a 500 nanometer thick coating, deposited at room temperature, and the substrate here is that platinum 10 iridium alloy. So you see when you're zoomed out pretty far that the coatings are fairly uniform. When you zoom in, you see these sort of elongated grains. So here this bar is 100 nanometers in length. On this slide, we're looking at the thickness dependence of the microstructure of the coatings. We have 2 different substrates, platinum 10 iridium in the upper 4 panels, MP35N in the lower 4 panels. The thicknesses range from 250 nanometers to 1,000 nanometers. In general, as you go from thin coatings to thicker coatings, the grain size increases. There are significant differences in the microstructure between the MP35N substrates and the platinum 10 iridium substrates at low thicknesses, and as the thickness increases, those differences seem to go away. On this slide are the X-ray diffraction spectra for the thickest coatings from the last slide. So if we look here, the lower curve represents the coating on platinum 10 iridium. The upper curve represents the coating on MP35N. If we focus on the iridium oxide peaks where there are no substrate peaks, for example here, the 110 peak, you'll see that the texturing in that orientation seems to be a little better on the platinum telluridium. Alternatively, if you look here at the 121 peak, the texturing seems to be better on the MP35N in that orientation than it is on the platinum telluridium. So it's clear from this spectra that these materials, these coatings, are not just randomly oriented, but they have a preferred texturing depending on the substrate. We made coatings at various temperatures, 20, 200, and 400 degrees Celsius, and they were all targeted to be 500 nanometers. If we look at the lowest temperature depositions, you see this sort of small grain that was reminiscent from what we've seen in the earlier slides. Then at 400 degrees, you see what look to be larger crystallites forming in the coatings due to the larger temperature and the higher mobility of the atoms when they're landing on the surface. But in between, we see this interesting surface microstructure. And if you look at the background here, you see something that is in between the grain size that you observe in the 20-degree samples and the 400-degree samples. It turns out that the microstructure that you see is dependent on the substrate that you look at. All three of these coatings were deposited simultaneously. The platinum telluridium shows lots of these platelets on the surface. MP35N shows a few that are nucleating, but not nearly the density. And then the stainless steel foil has even fewer and the nucleation of just a few of these platelets. This slide shows differences in microstructure based on thicknesses. So at 25 degrees, this upper panel here, you see the 250 nanometer thickness versus the 500 nanometer thickness. So more spherical grains to more elongated grains. Then at 200 degrees, we see that the grain sizes are a little bit larger here at the 250 nanometer thickness. But when we go to the 500 nanometer thickness, we see a lot of these surface structures, these platelets on the surface. This slide shows X-ray diffraction spectra for the various coatings at room temperature, 200C and 400C. It also shows the substrate. So here's the platinum telluridium plot, and you see as the temperature goes up, the iridium oxide peaks become sharper and taller. But what's unique about the 200 degrees C is there's this reflection here. The 011, which is not present in the 400 or the room temperature depositions. And there's only a hint of it shown here at the 200C and the MP35N, indicating that it's possible that those platelets are that orientation of crystal of the iridium oxide. As we continue the depositions, so here is the 250 nanometer coating made at 200 degrees C, and you don't see that peak, and the 011 peak. At 500 nanometers you see it, and then what we've done here to suppress it at 750 and 1000 nanometers is we've lowered the oxygen partial pressure, and we saw that we could suppress that formation. And so when the coatings get thicker, and at 250 you see these sort of larger grains and more organized grains than what we're seeing in the low temperature deposition. Ultimately, what we care about is the performance of these materials electrochemically. So we have an electrochemical cell here. Our sample, our coated sample, is the working electrode. A platinum coil is our counter electrode, and we have a reference electrode sitting in a phosphate buffered saline solution. We ramp up the voltage and we measure the current, and you expect to see this hysteresis-like behavior And when you integrate the area in the curve and do some further manipulations, you pull out this charge storage capacity. And what you see is at low temperature, you get the highest performance. Intermediate temperature, the performance is dropping, and at 400 degrees, it's dropping further yet. So the outlier is this one sample here, and that is the 200-degree sample with those platelets. So the difference between these materials and these materials are really those platelets. So the platelets forming increases the overall surface area, and as a result, improves the electrochemical performance dramatically. Knowing that the microstructure changes as you reduce the oxygen partial pressure, maybe increasing the oxygen partial pressure will form those platelets. So we went ahead and did those measurements, and here are two representative samples. There's 3 different magnifications of each of these, and you see at 35% oxygen partial pressure in the sputtering gas, you see these sort of thin platelets on their edges that look like a very high density of what we saw in the earlier slide at 200 degrees C. If you go down in partial pressure, you see slightly different microstructures, but reminiscent of what happened at 35. If we use the same cell and measure the electrochemical performance of these materials, we see that as the oxygen partial pressure increases, that so does the hysteresis enclosed in the 20th cycle here. So this is the 20th cyclic voltammogram. And what we see is that we get 59.3 millicoulombs per square centimeter for the materials that are deposited at 35% oxygen partial pressure. So every one of these materials with the platelets performs better, and as we increase the oxygen partial pressure, we continue to increase the performance, probably due to surface area. If we divide the performance of a flat coating into the performance of these coatings with the interesting microstructure on the surfaces, we see that we get 51 times the substrate area for the effective surface area of these coatings. This slide shows cross sections of the coatings. So here is the original sample deposited at 200 degrees C, where we first saw that interesting surface microstructure. So right here is the interface. There's a platinum 10 iridium substrate, iridium oxide, and on the surface, and you see a lot of curtaining effects, but if you look carefully at that interface, you'll see a layer between the platelets and the substrate. You can see it more clearly here on the sample deposited simultaneously on MP35N, and you see that there are far fewer platelets, but you see this layer which goes underneath these platelets here, and it's continuous. So there's some curtaining effects, so you have to use your imagination a little bit. But we went ahead and we made a fractured cross-section of a material that was on a witness sample on sapphire. So down here we have sapphire substrate. Here is the iridium oxide layer that forms before you start forming the platelets. And then this is the high density of platelets on the surface that occurs at the high oxygen partial pressures. So all of these materials show some evidence that there's a continuous layer of iridium oxide that forms before you start getting the platelets, that the platelets do not nucleate directly on the substrates. We presented the synthesis of iridium oxide by pulse DC reactive sputtering. At 200 degrees C, we saw these interesting surface platelets, which led to improved performance. At high oxygen partial pressures, we saw similar platelets, which also led to high performance. All of these are likely higher performing due to increased surface area. The platelet formation depends on temperature, thickness, substrate, oxygen partial pressure, and likely target poisoning, because we have some pretty high oxygen partial pressures. The thickness dependence comes in because you need to have a certain thickness before you can start nucleating the platelets, and we've provided significant evidence for that. Thank you very much for your attention.